So we just saw that for population growth or decay, we're gonna use exponential models. Now, we could use base 2, we could use base 3, we could use base 4, we could use base whatever you want for exponential models. However, it is more convenient to use base E, and it's because we're gonna be studying the growth rate of a population. So if the population is written as e to the x, then we know that derivative is simply e to the x, whereas the derivative of a model like this would be 2x times the natural log of 2, and here will be 3 to the x times natural log of 3 for the derivative. So it's adding an extra constant, and also this constant is not the same. It's dependent on the model that you're using. So it's really not convenient to use different bases. So we're going to stick with base E. Remember, that's the irrational number 2.7 blah 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 blah. Okay, so I'm just gonna call P for population, and we're gonna stick with T rather than X because the independent variable is gonna be time. So let's say that I'm using e to the t. Now this model is not enough, because if t is 0, then p of 0 is e to the 0, which is 1, and no population ever starts with only one individual or one bacteria or one atom, or whatever it is that we will be studying, or $1. So definitely we can't start with the parent function. We're gonna need some population at the beginning different from 1. So this population at the beginning, we're gonna denote it by p sub 0. So p sub 0 is population at time t equals 0. Okay, now it doesn't mean that we're only going to study from years 0 unknown. It just means that if your problem talks about 1976 as the beginning of time, then you will define 1976 as your 0, and then you will work from there. So okay, so p sub 0 is population at time t. So I can have my population as the population at the beginning times e to the t. So if I were to graph this point right here would be the population at time 0. So at 0 I have the population at the beginning. Okay, so this p of t is going to change to p sub 0 e of t. Now if we talk about population of people, if we talk about bunnies, if we talk about bugs, this number is going to vary according to the situation. However, even if we're talking about two different countries that have the same population at the beginning, they may not change in the same way. For example, this one reaches after 10 years this much, okay, and then there may be other one that after 10 years reaches this much. So there's gotta be some way to accommodate this into this equation. So not only that the p sub 0, or the population at the beginning, could be the same, but after some future years it needs to accommodate the fact that it may be different. So for that, instead of having a vertical dilation, we're going to have a horizontal dilation to accommodate for that future point. So in that case, for a horizontal dilation, I'm going to have some number multiplying my independent variable, as you know from transformations. So this is the general function that we're going to use for population. Now it could be that k is positive, and in that case we're talking about exponential growth. Okay, the population is growing by 12%, so more people as time goes by. Now let's say that that population got Ebola. Then definitely the rate at which this population is decreasing is going to be some number less than 0. So in that case, we're talking about exponential decay. So by transformations, if we're talking about an equation, I don't know, let's say 20e to the 2t, then if this one is decaying at the same rate, this one will look like 20e to the negative 2t. Remember that the relationship between these two functions, since the only difference is the sign of the exponent, it will be a reflection over the y-axis. If the negative sign was in front, then it will be over the x-axis, but we don't have that case. We will only have initial population positive numbers, and this may or may not be positive or negative. So let's do a small example to see what it is that we're talking about. Let's have an initial population of 200. If this is a situation where the growth rate is proportional to the population size, and we're going to extend on this idea later on. I know that it really doesn't mean a lot to you right now, but we will explore that idea, which is very important later. And it grows 50% per year. So knowing these three facts, this idea is kind of like saying a function is continuous when we studied it in pre-calculus, and it may not have meant a lot to you, but now it means a lot more than it did before. So I promise after these videos this is going to mean a lot more to you than it does now. Okay, so with these three pieces of information, I can write an equation for population. So population at any given time will be given by 200, which is the initial population, E. Since it grows 50% per year, then this is going to be 0.5 t. Okay, so if after 1 year I replace 1 here, so the population after 1 year will be 200 e to the 0.5. Population after 2 years will be p of 2, 200 e to the 0.5, times 2. P of 3, 200 e to the 0.5 times 3. Now remember that when you're solving this kind of problems, you have to follow order of operations. In this case, the multiplication will be done first, then e to that power, and then that answer multiplied by 200. So let's see, let's look at different results, and let's look at the graph of this. So you see how we're gonna use t. This presentation uses x, but it is the same idea. It's using base e. So I have the graph of this function, how the population increases. So at the beginning of time we have 200 people, and then by the next year we have 329.7. Now remember that these are approximate values, so we're gonna keep the decimals unless otherwise noted. You know that it doesn't make sense to have 0.7 of a person, but you don't know where these numbers are gonna go to after we study them with mathematics, so we're gonna keep the decimals. Year 2 is 543.7, year 3 896.3, year 4 1477.8, and then naturally as the years go by, then the population keeps growing, and it's growing faster and faster and faster. So the rate of change between any 2 consecutive years is gonna grow fast. So unless we're talking average growth, or average rate of change, or average growth, whenever I say, or whenever you read growth rate, you're gonna think about how the population changes instantly. Okay, so this is the term for instantaneous rate of change. So to find the instantaneous rate of change, or to find the growth change, the growth rate, I'm sorry, for this function, I just have to take the derivative, as you know by now. So I want to know how the population changes respect to time. So when I want to know how the population changes respect to time, I'm taking the derivative respect to time, which is p prime of t. And then p prime of t will make me take the derivative. 200 is a constant and it's multiplying this function, so I'm just going to take the derivative of that function, which is itself. And then by chain rule, I have to multiply that by the derivative of this mini function of t, which is 0.5. So let me just rearrange this. P prime of t is 0.5 times 200 e to the 0.5t. But let's look at something interesting here. This is nothing but the original equation. So I could say that this is 0.5 times p of t. So now let's read it again. The growth rate is a number, okay, times the current population. Now when that happens, when a number is a constant times another number, those two quantities that change are said to be proportional. For example, if I know that I have a triangle where one side is 2 and I have another triangle whose side is 8, and I know that these two are proportional, that means that if the other side is 1, then this side must be 4, because the relationship is times 4. So this side would be 1 times 4 is 4, then this side would be times 4 will be 12. So anytime a number times a constant gives me another number, they are said that it's proportional. So in here I can say the same thing. I can say the growth rate is proportional to the current population, which is nothing but what we have said earlier on. The growth rate is proportional to the population size. So so from what we saw in the graph, you know that this change, okay, it changes. You know the current population changes with t, and then this is the only number that stays the same, that is constant. So now this is these calculations come from the example, but what happens in general if I have a model for population that looks like p sub 0 or initial population e to some number, I'm gonna call it k t, then I take the derivative, which is the growth rate. So now this is growth rate, and I'm taking the derivative of this, which will be itself, times the derivative of kt, which is k, and rearranging, I have k times p sub 0 e to the kt. You know that this is p of t. So now the growth rate is proportional to the current population. Okay, so the name of this k is going to be relative growth rate, and it's relative because it's the one that gets multiplied by the current population to give you the growth rate. So growth rate is relative growth rate times the current population. Okay, so let's say it again. Growth rate is relative growth rate times the current population.